Today I'm going to talk about noncoherent task tracking in mmWave systems. Um, we see so many multimedia applications like virtual reality, augmented reality that require multi-gigabit per second data rate. And also tech companies are forecasting increase in data demand in the near future. And we know that today's Wi-Fi and cellular network are not going to afford this increase in data demand. So the next generation of cellular networks, 5G, is going to address this issue. And we see it under the name of 1000x cellular, which means we are shooting for increasing the capacity as much as 1,000 times what we have right now. Um, so one of the most effective ways to provide this much increase in capacity is going to millimeter wave path. Because first of all, it will provide us with much higher bandwidth. We can easily have multi-gigahertz bandwidth. Also, since the wavelength is very small at millimeter wave band, we can put much larger number of antenna elements in small form factors, and that way we will be having beamforming gain, and by that focusing energy towards the user, and that means we can extend the range of millimeter wave communication for outdoor applications as well, like cellular networks, as well as since we are minimizing the interference this way, we can have multiple links at the same time, serve multiple users at the same time, and increasing the spatial range factor. But the problem with these tensor beams that focus the energy toward the user is that we need to identify the path to the user on the fly. Because, for example, these beams can easily be blocked by other pedestrians or the user itself, and we need to switch to some other path to have a robust link. Also, when the user is moving, we need to realign the beam toward the user. So we need a very efficient way of tracking the path and to maintain a robust link despite the mobility of the user. Also solve the blockage problem. For example, the user itself can turn around and block the link to itself. And also, as I said, we want to serve multiple users at the same time. So base station probably should be coordinated to manage the interference that they're introducing for other users. Also, when the user is moving from one base station to the other one, we need to handle the handover. All of this suggests that we need some algorithm to track the different tasks to the users. And it needs to be very efficient and quick because we need to repeat this tracking phase. Um, for example, and how rapid we need to track the user depends on the velocity of the user that you're tracking and the beam width of the antenna. For example, for a vehicle that have 25 meter per second velocity and a 16 element antenna, we need to do this every 10 milliseconds. So we have this tracking phase, and then we'll send the data over the communication phase. In order to minimize the overhead, we need to minimize this tracking phase. So for example, in this case, we need to do this tracking phase in less than 1 millisecond in order to have a low overhead. So we said that there is a huge potential at millimeter wave band for increasing the capacity, but one of the main barriers to utilize this capacity is having some algorithm to track the user. And I'll mention some of the conventional approaches, traditional ways to do this path tracking, and I'll say that what are the shortcomings in case of millimeter wave band. And then I'll go to our contribution, which is the noncoherent compressive measure, and we'll show the our tested results. So one of these conventional approaches is exhaustive scanning. So we will try each and every direction, and then based on the feedback from the user, we will decide which direction which user is at. But it doesn't scale with the number of antenna. As I said, we want to have large number of antenna elements in millimeter wave. And the number of directions that we need to scan is increasing linearly with n, and that means too much overhead. The other approach is hierarchical scanning, which is borrowing the idea of binary search. So we are starting with wider beams, covering more area, and then based on the feedback from the user, we will decide which region to get the narrower feedback from the user. And then we'll continue this approach until we find the user the exact direction. But the problem is that we need to wait for the user to send us feedback, and based on that, we'll decide the next beat. And that is introducing too much overhead. Also, it doesn't scale with the number of users. As I said, we want to serve multiple users at the same time. And if we had, for example, one user over here and one over there, we need to scan both of the regions. So it doesn't scale with number of users as well. But what is our suggestion? First, I need to explain the idea of compressive sensing, that we are borrowing this idea to develop a framework for channel estimation in millimeter wave. The idea of compressive sensing is saying that if we have a high dimensional signal, for example, X, then we know that this signal is sparse in some specific domain. For example, this multiplication, the signal X is not sparse, but when we take the Fourier transform, it will be sparse in frequency domain. If we have such a signal, with a randomized projection of this signal to some subspace, which have a dimension smaller than n, we can recover these sparse elements. This is the whole idea of compressive sensing. And how can we apply this to our problem that we have large number of antenna elements, so the dimension of the millimeter wave channel is large. But we know that we, according to characteristic of the millimeter wave channel, we have a few number of paths. So it's going to be sparse in angular domain or spatial frequency domain. Okay, so can we apply that compressive sensing idea to make these sparse elements? And the answer is yes. So these random projections are random patterns that we're designing to capture the feedback from the user. So we are spraying power in different directions randomly. And it's not like the scanning approaches that there is some peaks at some angular frequency. So we're spraying power, and then based on the feedback from the user, this Y feedback, we will deduce the angle of the user. And for example, this graph is showing the result of this approach. So for example, if the true frequency where the user is this shown in the horizontal angle, based on the template matching that we have done for different hypotheses, we have this y equals x as the maximum of this graph, which means we have effectively find the angular direction of the user. This approach is the overhead is it's efficient. The overhead is small because it's scalable with the number of antenna, log n, and it's scalable with the number of users because the same patterns are being sent for all of the users. We don't need to do anything extra for more number of users. And then after we have sent all the beacons, the users will send one packet of the feedback as the received signal. Also, it will support coarse space control, which I will discuss later. So everything is fine with this approach. But when we wanted to implement it with our testbed, we realized that we have a problem of transmitter and receiver are not synchronized. So there is this offset between the local oscillator of the transmitter and receiver, which will introduce a random phase to the received signal. So this YI signal that we wanted from the user to feed back to the basis station, the phase of that signal is corrupt. So we cannot rely on the phase of that signal. So we need to design or adjust our algorithm such as it will work just with the RSS of the signal. And the question is, if we only feedback rely on the absolute value of this Y, is this algorithm going to work for this case? And the answer is yes. We extended this algorithm for the RSS-based case, and then we did this template matching again, correlating the RSS of the received feedback signal to the RSS of what we expected from different angles. And then this is the result. So you can see this is the result for the coherent one that we had access to the phase. And this is the result for the non-coherent, which is 32 beacons. And you can see that it's a little bit noisier, but still the Y2 is the maximum, so you can effectively find the task. Also, there are some other hardware constraints, like these phase shifters that we are designing the pattern with. Since we don't have as number of RF chains as the number of antenna elements, we need to do everything in the RF domain. So these phase shifters should be implemented in RF domain with delay length. And that is not that is expensive. So we need to have our algorithm needs to be robust to the phase control quantization. And our approach, since it will spray power in every direction randomly, it's not sensitive to this error. But other scanning approach that need to design these beams toward a specific user, a specific direction, that will be more vulnerable to this coarse phase control. So I'm showing the experimental result. So we had this setup, this 16 by 8 antenna array, and we could just do steering in horizontal direction with 16 elements. And this is, for example, one of the scenarios on our business campus that we emulated the cellular case. This is, for example, the base station, which is higher than this is emulating the mobile user. And so, for example, we captured the channel with exhaustive scanning, and this is the result for that with 64 beacons. And then this is the cost function of our proposed approach with 16 and 32 beacons. And you see that the dominant path is exactly recovered. And then we did the experiment for multiple locations on the campus, and this is the statistical result of that. You can see with both 2-bit and 4-bit quantization control over the phase, we could recover the dominant path with only 15 beacons. And then this is the case for both the single pass and the 2-pass scenario. When in 2-pass, for example, one of the line of sight or one of the paths is the dominant one. So also this is showing the simulation result for how our algorithm overhead scale with the number of antennas. For example, the exhaustive scan is scaling linearly with the number of antennas, the overhead, the number of beacons. But our algorithm is scaling with log n, which doesn't introduce too much overhead. So, as a conclusion, we have found compressive estimation a promising approach to estimate and track the path, because it has a low overhead, it scales well with the number of users, number of antenna, and it's compatible with coarse phase control. But the only problem with this approach was that it couldn't work with off-the-shelf 60 GHz or mmWave devices, because we couldn't have access to the phase of the receipt signal. So we adjusted this algorithm to work with the RSS values only. And now we are developing some approach for multi-pass scenarios as well, but that is going to be published soon. And I would like to answer your questions. Thank you.